Today we're talking about exponential functions. So exponential functions are any function that has this form of y equals a times b to the x, where a, b, and x are all real numbers. The domain for all of these functions will be negative infinity to infinity. That means all real numbers. The range will be y is greater than 0. Notice that it's not equal to, that means it won't ever hit the x-axis in standard form. You can also write that in interval notation, which would be 0 to infinity. And make sure you note that I use the parenthesis this time and not a bracket. So we have our two pictures here. The first one is a picture of a growth, and that's because it's going up as you go from left to right. The second one here is a decay, and it's because you're going down as you go left to right. The way you can distinguish between them, if you're just looking at the equation, is right here, where it says b is greater than 0. If I have a 2 to the x like we do below, this would be called a growth. But if it's a fraction like 1/2 to the x, then that's going to give us a decay function. You can always plug your equation into Desmos to check which way the function's going. So if it's going up, you're going to say growth. If it's going down, you're going to say decay. So down here, some actual tablets. If you type all these into your calculator and we plot the points down here, you'll see what the picture is. You also can always do this in Desmos. As you can see in the table here, I just typed it in, so I got a fourth, a half, 1, 2, 4, 8, and I plotted the dots and connected it down here. You can do the same thing for the next table. I did the math for you. Got 16, 4, 1, 1/4, 1/16, 1/64. You can get all of these also in decimal form by plugging it into your calculator. So if you connect all these, you should say that this one is now going to be going down as you go to the right. So the difference between your two functions here is this one right here, you notice is going up, and that's because the base was a 2. And this one right here, your base is a 1/4, which is less than 1. That's why the second picture is going down as you graph it. And the third one here, the only difference for this one is that there's a 3 out in front. So let's see what that 3 is going to actually do to our function. So as you can see in this chart here, you get the answers from the first chart over here, but you multiply them all by 3. So that's how I got the 3/4, the 3/2. I'm just multiplying all these by 3. So when you connect these here, you should see the change here is that my y-intercept has now become a 3, whereas over here, my y-intercept was a 1. So the 3 in front, that's your a value, that will determine where it hits on the y-axis. So down here, the x-intercept, there should never be an x-intercept in standard form. So these are all going to have none. There's no intercept, no x-intercept. And then again, the y-intercept is what was the number in front. So here's a 1. It hits at 1, hits at 1, and this one now hits at 3. On your next page, when you have a function here in standard form, we just said a was the y-intercept. Now h and k tell us how our graph's going to be moving. So h always moves our graph left and right, and k is going to be moving your graph up and down. It all depends on your function. So an example here on a says x minus 2. This is considered a positive h because the equation already says minus. So this is going to move our graph right, whereas b is an example of it being negative, and this moves our graph left. Also, a tells us the direction that we're opening, not just where your y-intercept is. So if a is less than 1, then that's going to reflect our graph. And then this is just if it's stretching or compressing. So bigger than 1 will stretch the graph. That's what we noticed with 3. And this one will compress it. What we noticed if we put a 1/2 out in front of it. K is going to move your graph up and down. If I have a 3 to the x and there's a +2 out here, that will move it up. But if it had said like -5, that moves our graph down. The next examples, we're just going to state what kind of movement it has. Right here, you'll see that it says x minus 2. Remember, that's opposite, so we're going to go right 2. This is not up in the exponent, so that's an up and down motion. This is going to go down 2. The last movement we have here is that negative out in front. That's going to reflect it over the x-axis. So you should notice your graph is pointing in the other direction. Now, if you want to be able to tell if these are growth or decay, you might want to take a second and plug them into Desmos, or you can look at the number that has the x in front of it, and that will tell us if it's a growth or decay. So 1/4 to the x That's going to be a decay. 2 makes it a growth. A 1 to the x. The rule is all about 1, so this is neither here. This was a trick for you guys. So go ahead and take a second to try to do them yourself. Now this is a growth. This is neither. And this is also a decay. If you recall what f of 2 means from our earlier lessons, that means that x equals 2, we need to plug it in to get our y. So down here, if I want to find f of 2, you're going to plug into your calculator or into Desmos this function here. So I plugged this in and I hit equals into my calculator and I got out 4. If I wanted to do 0, I just change this to a 0 now, and that will give you out 1.75. And if you wanted to do the 4, you just change to a 4 right here. It's a 4 minus 2 up there, and that's going to give you 13. So AIR is going to give you questions where they give you a table of values, and you're going to have to distinguish between if it's linear or if it's exponential. We already know the difference between equations. So if you have an equation, the difference between linear and exponential is linear, it's just like ax plus b. There's no exponents anywhere. That would be linear. The exponential we just talked about, there's an x up in the exponent here. So that's what makes this exponential. When we're given table values, we don't have that nice luxury of just looking at an equation. So there's little simple rules. If you're going to have a linear equation, you're going to be able to find the same difference between each value, which means if I add the same number each time, we're going to call it linear. Now, if I multiply or divide by the same number each time, and that's what we're going to call exponential. So let's go ahead and figure out the difference between these, and we're going to figure out if they multiply and if it adds the same number, if it multiplies the same number. So as you can see, I went ahead and added for you. So when we add, we get a 0.1, a 0.2, and a 0.4. So that's not the same number each time, so it can't be linear. So then I check, do I multiply? And so I notice if you divide these two numbers, you get 2. Divide these two numbers, you get 2. Divide these two numbers, you get 2. That means that you're multiplying by the same number each time. So this right here would be an example of an exponential function. And then we check over here with number 2 and do the same stuff. So I noticed I added 3 each time, so I don't even have to check if the division works. So this has to be linear over here. So on this one, I noticed that I add 1, and I add 2, and add 4 again. That can't be linear. So we would check to see if we divide, if we get the same number. I went ahead here, now I divide each of these terms, I'm getting the same number. So again, that's called exponential. And then on number 4, I went ahead and I saw that I was adding a -3, like each one's decreasing by 3. This is going to be an example of a linear equation.